Test, test. Good evening, everyone. My name is Davis Jewell, and I want to extend a warm welcome to each and every one of you. Thank you for joining us here today for the Lethbridge-hosted Machine Learning Introduction Workshop. Before I begin, I'm going to play a territorial land acknowledgement delivered by an elder from Piikani Nation.
Oki, and welcome to the University of Lethbridge. Our university's Blackfoot name is Iniskim, meaning Sacred Buffalo Stone. The University of Lethbridge acknowledges and deeply appreciates the Siksikaitsitapi's connection to their traditional territory. We as people living and benefiting from the Blackfoot Confederacy traditional territory honor the tradition of people who have cared for this land since time immemorial. We recognize the diverse population of Aboriginal people who attended the University of Lethbridge and the contribution these Aboriginal people have made in shaping and strengthening the university community in the past, present, and in the future.
I'd like to say we are also truly grateful for your participation and interest in natHACKS. I can speak on behalf of all organizers, I think, that we're really looking forward to seeing you all at natHACKS. But without further ado, I'm going to dive straight into this. So here's the definition of what is machine learning, attributed to Arthur Samuel. He defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. Samuel's claim to fame was that back in the 1950s, he wrote a checkers playing program. The amazing thing about this program was that Arthur Samuel himself wasn't a very good checkers player. What he did was he had programmed the computer to play maybe tens of thousands of games against itself. By watching what sorts of positions led to good positions, or to wins, and what sort of positions tend to lead to losses, or bad positions, it learned to get better and better over time. It did this because it had the patience to play tens of thousands of games against itself, and was able to get so much playing experience that eventually it became a better checkers player than Arthur Samuel himself. For anybody that I haven't met, I'm Davis. I run the Lethbridge division of NeurAlbertaTech. I'm also a master's in neuroscience student, studying under Dr. Wishaw here at the Canadian Centre for Behavioral Neuroscience. The thing that we're going to spend the most amount of time on in this workshop particularly is practical advice for applying machine learning algorithms. We're not going to touch so much so on the math. That's going to have to be something that you pick up mostly by yourself, and I don't think you can truly fully cover everything that is machine learning in the span of a single workshop. So ideally, I wanted to teach an interest in machine learning and teach the applications of it. Teaching solely the base code of machine learning is like giving someone a new set of tools that they might not necessarily know how to use. And I feel quite strongly about this. It's far more important to teach how and when to apply these new tools. Because for instance, let's say I just give you a hammer and a drill and tell you, build a 3-story house now. You have all the tools you need after all. Unfortunately, it doesn't really work like that, so it's important to know when and how each of these specialized tools can be used most effectively. Otherwise, I'm just pushing you off in the deep end. I also think, anecdotally, to fully learn about something, you also have to be passionate about it. So I'm going to try and do my best to convey kind of the coolness aspect of machine learning. Already failing to do so. So we're going to begin with an overview of machine learning. touch on the types of, well, 2 of the 3 main types of machine learning, supervised and unsupervised learning, touch on how gradient descent can be applied to both of these, and then the field of neural networks, I guess, from a biological perspective, as that's kind of what I come from in neuroscience. I'll just get started on that here. So just to expand on Arthur Samuel's definition a bit, machine learning is the field of study that focuses on the development of algorithms and models that can learn and also make predictions or decisions without being explicitly programmed. I like this slightly more empirical definition because it also postulates that all machine learning algorithms have some sort of agency to make predictions or decisions on their own. Although it is important to note that machine learning is itself not artificial intelligence, it is only a subset, even though we are quite still far off from what may be called a generalized artificial intelligence. Most current systems operate as a particular type of intelligence, but find different ways to mask that fact. There are plenty of useful libraries and frameworks that I'd recommend using when starting to build and train machine learning models, so I just kind of wanted to list them here for anybody that wants to just take those and fly with it and that feel proficient in coding already. But to list a few, there's TensorFlow, PyTorch, and scikit-learn. All of them are quite handy. But I also wanted to include just a specific list of some types of machine learning algorithms. You don't need to know all of these, but I just wanted to give them an example for how it can be difficult to select the correct machine learning algorithm to use. Because for instance, that list was by no means exhaustive, and yet you can still probably see that there's a good enough amount of them that it can be quite difficult to know which is the right algorithm to apply to a particular problem. And so knowing how to select the appropriate algorithm is really what distinguishes machine learning experts and really what will save you time. The problem in almost all cases, I think there might be some exceptions, but the problem in a lot of cases isn't so simple as copy paste. If it was, I could just give you this string of code, but like I said, it's just not that simple. This is what your average ML workflow will look like. The by far lengthiest portion of time is during model training, stuck right here in the middle. This really sucks because if you select the wrong model to use, you'll spend a lot of time in training only to have your model show a bad performance and have it refuted, needing to go back to selecting a new model all over again. However, if you select the appropriate model, you'll go straight through and save lots of time. So I'm sure that you can see how this will save you time by selecting the correct model from the start, and that way your model won't need constant revision. Another thing that you might run across is just messy data in general. Since this doesn't always involve machine learning algorithm use itself, I'm going to pass over it more than it merits the time for, but I definitely recommend looking into data pre-processing techniques on your own. The overall goal of data pre-processing is to transform data into another data set, which is better suited for machine learning. So for instance, in the real world, you might run across null values and non-numeric data that you include in your spreadsheet. These will need to be eliminated if you want to use a machine learning model. There are 3 main types of machine learning. Supervised and unsupervised are by far the most common, and so I'll focus on these for the purposes of this workshop, which is limited by time. In supervised learning, the model is trained on labeled data, where the input is paired with the corresponding output labels. And in unsupervised learning, the model is trained on unlabeled data, where the input does not have any corresponding output labels. Lastly, there is reinforcement learning, where the model learns by interacting with the environment and receiving feedback in the form of rewards or penalties, but unfortunately I won't have the time to cover it today. And so we will cover supervised and unsupervised learning now. Between the two, supervised learning is the type of machine learning that is used most in many real-world applications and has seen the most rapid advancements and innovation. Main difference between supervised and unsupervised learning is the presence or absence of labeled data. Beyond that, The goal of supervised learning is to learn a mapping function from the input data to the output labels so that we can predict the correct output for new, unseen input data. Whereas the goal for unsupervised learning is to find patterns, structures, or relationships in the data without any prior knowledge or guidance. You can kind of see visualizations of each of these in the depictions below. Supervised learning is clearly labeled either as a 0 or as an X, whereas unsupervised is completely unlabeled. Two major types of supervised learning are regression and classification. In a regression application, like predicting the price of a house based on its size, the learning algorithm must predict numbers from infinitely possible outputs. Whereas in a classification application, such as diagnosing a neurological condition, the learning algorithm must predict a category of a far smaller set of possible outputs. Linear regression is a popular supervised learning algorithm used to model the relationship between a dependent variable and one or more independent variables. The equation for linear regression is given by a formula I'm sure everyone's familiar with, the slope-intercept form of a straight line, y equals mx plus b, where y is the dependent variable, x is the independent variable, m the slope of the line, and b the y-intercept. It is an example of supervised learning because we give the algorithm a data set in which the correct y plot is given for every value of x. The task of the learning algorithm is to then predict more of these correct answers, namely correct y values, based on the slope calculated from the given data set. And of course, because the number of its outputs can be infinite, linear regression is a form of regression. Then we also have classification algorithms. Logistic regression, rather counterintuitively, is a type of classification algorithm. It is basically just a modified version of linear regression, so we still attach a part of the name to it, but it is, as a matter of fact, a classification algorithm, even though its name might lend to some confusion. Here is an example of linear regression. Here is an example of logistic regression. A classic example of linear regression is to use house statistics like square footage, age, neighborhood, crime rate, etc. to predict the listing price of the house as y. Let's specifically look at an example relationship between square footage and listing price. So here, x is square footage and y is listing price. So imagine the square footage of the house as x and the listing price as y on this graph to the right. Intuitively, we can see that, generally, the bigger the house, the more expensive it is. We can also see that the data is approximately linear, so we can draw a line through the data that approximately represents price versus square footage. We can then use this line to predict the price of a house given its square footage. This line, or more specifically the equation representing it, is a very rudimentary machine learning model. So let's start where everyone should be familiar with the slope-intercept form of a straight line, y equals mx plus b. In linear regression, y equals mx plus b turns into function f of x equals wx plus b. The values chosen for w and b will determine the prediction y hat based on the input feature x. And by convention, y hat is an estimate, and just straight y is the actual true value in the dataset. Univariate linear regression can be implemented in Python code as such, base code at least. You import NumPy, set some set of values, and then create this simple for loop. And that's really all you need to get it working. If we even go on to make a graph of this, we can see that the line, the slope, fits exactly, at least for this particular data set. But what happens if we add in new data? So here we're adding in a new value of a new value of x that represents a 1,200 square foot house, not square meter. And as you can see, if we make a prediction, the new value fits into our slope as desired. So with just a few lines of code, we are able to get a functional machine learning algorithm. And you can see if we just run it on a calculator, we get the value. It will be, the house should cost $340,000, and that is indeed the case that our model predicts. But again, what if we wanted to quantify our performance on predicting new data? So to assess the accuracy of your machine learning algorithm, in this case linear regression, you'll need to use some form of performance assessment. This is what the cost function will do. It will tell us how the model is doing so that we can try to get it to do better. Recall that you have a training set that contains input features x and output targets y. The model you're going to use to fit this training set is this linear function fw b of x equal to w times x plus b. To introduce a little bit more terminology, w and b are called the parameters. In machine learning, parameters are the variables you can adjust during training in order to improve the models. And sometimes you also hear the parameters w and b referred to as coefficients or weights. Again, skipping over the math used to derive this formula, here we describe the cost function formula for linear regression. Here we're going to write function j of w to refer to the cost function, and this is also called the squared error cost function, and it's called this because you're taking the square of these error terms just right here. In machine learning, different people will use different cost functions for different applications, but the squared error cost function is by far the most commonly used one for linear regression, and for that matter, all regression problems where it seems to give good results for many applications. The squared error cost function formula can be implemented in code as follows. The code on the right calculates the cost by looping over each example. In each loop, a prediction FWB is calculated. The difference between the target and the prediction is calculated and squared, and this is added to the total cost. We will talk more about the importance of minimizing the cost function when we get to our topic on gradient descent. And so that's it for linear regression, at least. On to logistic regression, which again, to reiterate, is, as a matter of fact, classification as opposed to regression. Logistic regression is probably the single most widely used classification algorithm in the world. For our purposes, let's think of an example of diagnosing a neurological condition, such as classifying a brain tumor as malignant or benign. We can use the labels 1 or 0. We can use the label 1 or yes to the positive class representing malignant tumors, or 0 or no negative examples to represent benign tumors. So you can see this kind of S-curve that will develop as that model is trained. So I'm going to breeze past the math for logistic regression, but what you need to know is that the sigmoid activation function transforms linear regression equation into a nonlinear equation, allowing it to model more complex relationships between the variable and sort the data into two discrete and simple categories based on the value of z around a line set at 0. You can see a depiction of this just right here. So if you think you want a quite clear distinction between a benign or a malignant tumor, since it is a classification problem, And that's exactly what you will see with the sigmoid function. This is what the sigmoid function changes from linear regression. Function f of w and b turns into a value z down here. And then that turns into the logistic function g of z equals 1 over 1 plus e to the power of negative z. Logistic regression can be implemented in code as such. So similarly, you set NumPy, define what the sigmoid function is, and return function g. So now I can show you an example of how we might do this in code particularly. So again, you begin, just import NumPy and any other libraries that you might need. You can, or you will, set a NumPy array. In this case, they're just displaying the values. Define the sigmoid function to return g. Here they use that function they defined as sigmoid to estimate another additional range and visualize it as such. But what if, in our own data set, such as defined here, we want to calculate the logistic regression on a logistic regression model on categorical data? So we can run this with a simple click from this kind of code here. And I'll just do that to show you what it'll look like. You will see, as opposed to the example of linear regression on categorical data I'm going to show you in a second, if you add more data, even in the higher range of this, of tumor size, you won't see any significant deviation from the original z value that was calculated. Whereas, if we do the same in a linear regression model on categorical data, in the first place, it won't be quite as accurate. As a matter of fact, a decent chunk of malignant tumors might be considered benign in this case, which to start with is quite a horrible model. But if we also add further data downstream, we'll see that it will only get worse, and even more tumors will be considered benign when they are, as a matter of fact, malignant. So remember that to assess the accuracy of your machine learning algorithm, we used the cost function formula for linear regression, but in this case, for logistic regression, you'll need to use some form of performance assessment, and here we describe two different formulas for logistic regression. Because when applied to classifications such as logistic regression, the squared error cost function produces a non-convex plot, which when we begin to cover gradient descent, I will begin to explain to you why a non-convex plot is not ideal. But we can change the original squared cost function formula to the logistic loss function formula. This is what this describes here, where instead of cost, loss denoted via the capital L replaces it. However, the simplified cost function formula is the one that I really want you to know, as it's just a simpler way to write out the loss and cost functions, and can be quite a bit simpler when we get to gradient descent. There's quite a bit of math behind how we get to this formula. So again, it's something I have to admit But if it's something that interests you, I'd definitely recommend checking it out. And I'd just like to mention that this particular cost function is derived from statistics using a principle called maximum likelihood estimation, which is an idea on how to efficiently find parameters for different models. This function has the nice property that it is convex, which again is very useful when we get to gradient descent. The simplified cost function formula can be implemented for logistic regression as follows. However, the process overall remains similar. First, you import numpy, define the sigmoid function according to the aforementioned commands, return function g, and then you set the you set the number of training examples in the dataset m and n, and then compute the cost function using this string of code on the right. But that's how you would calculate both a linear regression and a logistic regression model. But both of those are considered supervised learning. So in case you forgot about it, we also have a different type of machine learning algorithm entirely, which is unsupervised machine learning. The three major types of unsupervised learning are clustering, dimensionality reduction, and anomaly detection. Clustering involves grouping similar data points together. In dimensionality reduction, we want to reduce the number of features or variables in the data, and in anomaly detection, we find unusual data points. So I'm going to focus mainly on clustering. K-means clustering is a method of vector quantization, originally from signal processing. It aims to partition n observations into k clusters, where each observation belongs to the cluster with the nearest mean. The algorithm calculates the distance between each data point and a centroid to assign it to a cluster. It is best used for statistical analysis, K-means clustering is relatively simple to implement and understand. While this makes it easy for beginners to grasp and apply the algorithm, this also makes it widely used for data segmentation due to the simplicity and straightforwardness. So I don't want to dive into K-means clustering in too much detail here, since there are already plenty of common implementations out there, such as the K-means function in MATLAB. Therefore, if your project involves a more complicated form of data segmentation than can be computed with logistic regression, I would highly recommend reading up on this, and the link for this, the MATLAB help link is just listed down here. And this is, of course, just a visualization of kind of the data that you would get. But with that, we're now ready to jump into gradient descent for supervised learning. As we have seen so far, you can use different functions to calculate cost depending on the application. However, it turns out that gradient descent is an algorithm that can use to try and minimize any function, not just the squared error cost function formula for linear regression or the simplified cost function formula for logistic regression. Very long words, but all you need to know is gradient descent can be applied to either and is just as functional in both, as long as you're using those respective formulae. Let's begin with defining the learning rate. In essence, the learning rate alpha controls how big of a step you take when updating the model parameters W and B. And there's also a term in here which might be absolutely terrifying to some people who recognize it, and that's the derivative term delta. That's a funny little D written here in font thing. In case anybody watching this has like a PhD in math or is an expert in multivariate calculus just on the side, they may want to point out, hey, that's not the derivative, that's actually the partial derivative. But for the purposes of this workshop, I'm sorry, I'm just going to call it the derivative. We're not going to worry about those distinctions for this moment here. On the right is an example of what gradient descent does on function j of w, the cost, with parameters w as the axis, x-axis, and jw as the y. What gradient descent will do is that it will update w to be w minus learning rate alpha, which is why you see kind of these minute steps as learning rate progresses. Just to repeat, what gradient descent will do is that it will update w to be w minus learning rate alpha times d over dw of jw, meaning that it will descend gradually in incrementally smaller steps, which is important because you want to be very exact once you're close to the minimum for cost. The learning rate alpha will have a huge impact on the efficiency of your gradient descent implementation. If it is too small, then the gradient descent will descend too slowly, such as will be seen here, and will require far too many iterations. If it is too large, then the gradient descent may actually lead to an increase and lead to divergence from the global cost minimum. Another problem we run across in gradient descent is the potential presence of local minima in the data set. What happens at local minima, so here we have two kind of examples of that. So what happens there? Well, whenever you reach a local minima, the slope of the line is 0, and thus the derivative term is 0. This means that if you're already at a local minima, gradient descent leaves w unchanged because it just updates the new value of w to be the same as the old one, and it leads to just gradient descent being stuck in each of these local minima. So what you want is a convex plot. As we just saw, one issue with gradient descent is that it can lead to a local minimum instead of a global minimum. But it turns out when you're using a squared error cost function with linear regression, or the simplified cost function with logistic regression, the cost function does not and never will have multiple local minima. It has a single global minimum because of its characteristic soup bowl shape. And again, to reiterate the point home, the technical term for this soup bowl is convex function. And here's the gradient descent algorithm for linear regression. You repeatedly carry out these updates to w and b until it converges. And remember that this function of x is a linear regression model. So at the end of the day, it's still equal to that vaguely slope-intercept form of straight line, y equals mx plus b, but we switch the terms around to y times x plus b. And you want to make sure that you update w and b simultaneously on each step, which is why this is depicted as a three-dimensional plot with w and b on the axes. So what does this look like if we go over in code? Well, again, I'll just begin by importing our libraries, setting our data set, and then we can begin to make a quite a simple cost function for linear regression. And then we can begin to implement gradient descent. This is a plot showing that. Sorry, I keep worrying that this is going to take longer for each line of code than it actually does. So here is the iteration, how the cost decreases with each iteration step. So we can see that we are, with gradient descent, finding a smaller and smaller cost function value. We're just This is a visualization of this. Contour plot of cost is what this is called, and the path of gradient descent. You can see that it approaches 0, which is kind of this section at the very center. This is, of course, visualized as a two-dimensional plot, but it's more complicated than that. That's all I wanted to show. Because, again, that was visualized two-dimensionally, but it is a three-dimensional form. So if you think this transformed into this, I hope it will make a lot more sense. All right, so the gradient descent algorithm for logistic regression is surprisingly similar to linear regression. So you can just apply the same method to make sure it also converges. However, as I've kind of said, that you can apply gradient descent to both logistic and linear regression, you might be wondering why it's the case that they can be implemented the same way, but they're still considered different, because they are. I know I was for sure confused about this when I first learned about it, so I'll just explain that here. But so even though these equations look the same, the reason that this is not linear regression is because the definition for the function of x has changed. So you see that here. In linear regression, the function of x is wx plus b. However, in logistic regression, the function of x is defined as the sigmoid function applied to wx plus b. Now, what happens when you actually get to applying gradient descent to logistic regression, which is kind of our last lab that we'll have here. So again, we start at a similar point, defining our libraries, data, and then a quick plot just to show what that looks like. Then we can implement gradient descent as such. Again, I'm skipping over code, but I am kind of running short on time. Here it's running over multiple iterations. I was kind of expecting the last one to take this long because that's kind of how gradient descent goes. Here is just a visualization of that, showing quite good categorization of data as either, in our case, benign or malignant. And here we will get an actual calculation of that. So I'll run it from the current location. Again, this is a three-dimensional plot calculated in a two-dimensional plane, but here we actually get to see the three-dimensional plot version of that. And we will see in live time as I believe the learning rate descends, so too does the cost function. And you'll also see the effect of this over iterations. And it comes to a final conclusion that this is the global minimum. Alrighty, and with that, that's our, we're on to our last topic. If there are any other questions on gradient descent or like supervised, unsupervised machine learning, I'm listing my email at the end. It's not something I expect to be gleamed at a first glance. So if you just listened to that and thought it was really interesting, I highly recommend looking into it on your own. I don't think you're going to totally grasp all the concepts at a first glance. But onto neural networks, which are quite a popular buzzword right now. But let's see who really understands what they are. So for a moment, I want to actually take a break from the realm of machine learning entirely and consider other ways to model brain activity. So What is computational neuroscience, and why should you care? Well, the textbook definition reads that it is a quantitative approach using biologically plausible mathematical models to mimic the development, structure, physiology, and cognitive abilities of the central nervous system in an effort to understand them. A decade after Hodgkin and Huxley proposed their biophysical model in the 1950s, which described the neural output, the action potential, in mathematical terms, Hubble and Wisely proposed that each cortical neuron could be thought of as a feature detector that fires when its preferred feature, the stimulus, passes a given threshold, the resting potential. Shortly after this, David Marr proposed a new computational approach for determining how functional groups of neurons within the hippocampus and neocortex interacted to store, process, and transmit information. And I want to be emphatic about the importance of this, because if nothing else, I hope that every listener here today, no matter their background in neuroscience, computer science, or engineering, can take away that computational models, such as machine learning or neural networks, can be used to frame completely novel hypotheses that can be directly tested with biological experimentation. And it is in this way that computational neuroscience, and neuroscience or biology in general, can inform each other and really grow as a result. Here we have the brain, the cerebellum, the brainstem, the cerebrum. It's composite neurons, so like pyramidal, bipolar, Purkinje cells, etc. There are so many different neurons in the brain that I don't even know them all. It's actually quite fascinating, I think. Cajal describes in his book The Beautiful Brain all the different neurons that you can run across. So if anybody's interested in that, I definitely recommend checking it out. But besides those, I can definitely tell you at least about the parts of the neuron, because I know that myself. So you have like the cell body, the dendrites, and then the axon. And it's along the membrane of the neurons that you'll find all these various ion channels. Everything that we know about learning comes down simply to the flow of ions across neuron membranes, which produce action potentials, which I think is just kind of crazy. However, when we're coming up or trying to come up with a feasible model that takes after the intelligence of the brain, it really makes me remember the following quote. All models are wrong, but some are useful. And this was coined by the statistician George Box. You have so many different types of neurons and even different types of glia, not shown here. So exactly replicating the brain is quite impossible. Add on to the fact that we don't totally understand it, it's just too complicated, which is a huge part of the reason why the brain is so fascinating, to me at least. But at the end of the day, we must oversimplify things to come up with a useful mathematical model for neural networks. Deep learning is a subdiscipline of computational neuroscience based on artificial neural networks that learn with training. Natural intelligence is displayed by animals based on their senses, neural circuitry, motor systems, and plasticity. In contrast, artificial intelligence is demonstrated purely by mathematical machines, so how do we get this to work? Well, neurons typically have different inputs. The input wires of a neuron are called dendrites, and they act like tendrils, forming many synapses with other nearby neurons. The neuron may then send electrical impulses along its axon to produce an output towards another nearby neuron across the synaptic junction. The artificial neural network represents neurons as nodes. The fundamental building block of artificial neural networks is basically a layer of neurons, or a layer of nodes. These can be called the input layers, the hidden layers, or the output layers. The main difference between a simple neural network and a deep learning neural network is the presence of multiple hidden layers. Multiple hidden layers in deep learning, only one in simple. I would absolutely love to dive further into this and potentially even discuss implementations for TensorFlow, but unfortunately we're reaching the tail end of our workshop today. So like I said before, here is my email address. I'd recommend reaching out to me if you have any questions. I'd really be honored if you find some motivation from this workshop to go off and learn more about machine learning because of it. And so I really want to make myself readily available to you. Other than that, here are my slides, and again, I am really excited to see how natHACKS turns out this year, and yeah, I wish you guys all the best.